We shall now move on to the next chapter, the p block elements. In this chapter, you will study about group 15, 16, 17 and 18 elements. Group 15 elements are nitrogen, phosphorus, arsenic, antimony, bismuth and moscovium. Group 16 elements are oxygen, sulfur, selenium, tellurium, polonium and livermorium. Group 17 elements are fluorine, chlorine, bromine, iodine, astatine and tennessine. Group 18 elements are helium, neon, argon, krypton, xenon, radon and oganesson. So let us start with group 15 elements. Among the group 15 elements, nitrogen and phosphorus are non-metals, whereas arsenic and antimony are metalloids. Bismuth and moscovium are metals. Nitrogen is present in the Earth's atmosphere. What percentage of nitrogen is present in the Earth's atmosphere? 78% by volume. Nitrogen is also present in the Earth's crust as sodium nitrate and potassium nitrate. It is also present as proteins in plants and animals. Phosphorus, it is present in phosphate rocks. It is present in the form of calcium fluoride and Ca9PO4 6 times. Phosphorus is present in bones as well as in living cells. It is also present as phosphoproteins in milk and eggs. Arsenic, antimony and bismuth are present in the form of sulfide minerals. Moscovium is a synthetic radioactive element. We shall now discuss about electronic configuration, atomic and ionic radii, ionization enthalpy and electronegativity of group 15 elements. We shall start with electronic configuration. Consider nitrogen, its atomic number is 7. So the electronic configuration can be written as 1s2, 2s2, 2p3. Phosphorus atomic number 15. So the electronic configuration is written as 1s2, 2s2, 2p6, 3s2, 3p3. Therefore, we can say that group 15 elements have ns2np3 general outer electronic configuration. Note that the p orbitals are half-filled. So, the electronic configuration of group 15 elements are therefore found to be highly stable. It is because of the half-filled p orbitals. Next, we shall discuss about atomic and ionic radii. As we move down the group, atomic size increases. There is an increase in the size as we move from nitrogen to phosphorus. But there is only a small increase in the size as we move from arsenic to bismuth. This is due to the presence of completely filled d and f orbitals. We shall now move on to ionization enthalpy. Ionization enthalpy decreases as we move down the group. It is because less amount of energy will be required if the electron is far away from the nucleus. And we know that as we move down the group, the atomic size increases. So because of gradual increase in size, ionization enthalpy decreases down the group. Ionization enthalpy of group 15 elements are found to be higher than the ionization enthalpy of group 14 elements. It is because of the extra stability of the half-filled p orbitals in the case of group 15 elements. It is also due to the small size of group 15 elements. Electronegativity of group 15 elements. It is found that electronegativity decreases down the group. Chemical properties of group 15 elements. You know that nitrogen is a diatomic gas, whereas other elements exist as solids. The metallic character increases down the group. You know that nitrogen is a non-metal, whereas bismuth is a metal. So metallic character increases as we move down the group. All these elements exhibit allotropy except nitrogen. Let us now discuss about chemical properties. First, consider oxidation state. These elements have ns2np3 outer electronic configuration. It means they have 5 electrons in their outermost shell. So they can get octet configuration by gaining 3 electrons. Therefore, these elements exhibit an oxidation state of -3 in their compounds. In a similar way, these elements can also lose either 3 electrons or lose 5 electrons present in the outermost shell. Thus, they can exhibit an oxidation state of either +3 or +5 in the compounds. The tendency to exhibit -3 oxidation state decreases as we move down the group. It is because as we move down the group, the atomic size increases and the metallic character increases. So because of these two reasons, the tendency to exhibit -3 oxidation state decreases as we move down the group. Now, out of +3 and +5 oxidation state, it is found that the stability of the +5 oxidation state decreases down the group. It is due to inert pair effect. Another important point is that nitrogen does not form compounds in +5 oxidation state. It is because nitrogen does not have d orbitals. Now consider the reaction 3HNO2, that is nitrous acid, giving nitric acid HNO3 plus H2O plus NO. In this particular reaction, the oxidation number of nitrogen changes from +3 to +5 as well as from +3 to +2. So there is both an increase in oxidation number and decrease in oxidation number with the same element, nitrogen. So this is considered as a disproportionation reaction. Now in the case of nitrogen, it is found that it can exhibit a maximum covalency of only 4. It is because only 4 orbitals are available for nitrogen for bonding. If we consider the electronic configuration of nitrogen, we will come to know that only the 2s and the 3 2p orbitals are available for bonding. So that is how we get 4 orbitals associated with nitrogen available for bonding. Thus, nitrogen exhibits a maximum covalency of only 4.